Then we are going to do neural machine translation for a while. Most of the few slides, I have already covered them in the course last year. So I'm going to be going through them really quickly, and then you can stop me and ask questions. So this is an assignment for you to watch this video. What are we doing when it comes to translation? Like any other machine learning problem, you have these 5 components. You need to identify your data. So our data are going to be pairs of source sentences and target sentences, English, French. So we know what our data is going to be. And then it's actually your exercises to download some data and explore them. We write a model. In this case, the model is going to be in the form of a recurrent neural network encoder-decoder type of architecture. So you write a model, then you need to write a loss function, which is usually coming out of your likelihood. You basically try to maximize your likelihood or minimize the negative of the log of your likelihood. So that's your loss function. Then you're going to look at your training data and train the model. Then you need to measure the performance of your model. How good is your model? How good are the translation coming out of a machine translation system? How do you measure it? And in this case, that's going to be blue score. The next step is, again, using your validation data and this score, in this case, blue score, you try to come up with hyperparameters of your model. So you're going to do, and usually we call that AutoML. And the idea is you are trying to say, what should be the width of my neural network? How deep it should be? How wide it should be? What should be my learning rate? For instance, we just saw the slanted triangular learning rate. Where did that come from? It comes from a lot of experimentation. And those experimentations, you usually use your blue score or a score, performance metric, and then you come up with the best hyperparameters for your neural network architecture. And once that's done, it is done. You can take your model to production. You can actually use this translation system, put it on Google Translate, and then millions of users are going to be using it. But then you have to be careful. You cannot just rush into taking that algorithm and putting it into production, because if something goes wrong, your customers are going to end up being really unhappy. You first test your algorithm on the test data. You test it once. If you're happy, you move on to production. And this paper has all of them. What is the task? It's going to be translation. Somebody gives us a source sentence. We need to decode it into a target sentence, turn English to French. And this is a task that we appreciate. We understand it a lot. And the way that you're going to model it is, as soon as you know the probability of a target sentence or your target sentences, given an input sentence, you're going to be able to solve this argmax problem. Over all of the possible sentences, give me the best one. And then this step, we usually use a beam search type of algorithm. And then you're going to do your prediction one word at a time. Given the entire source sentence, predict the first word of the translation, pick 10 of those translated words, then go to the next step. You want to predict the next word in your translation. For instance, you predicted la here or el here. The next word is going to be accord. To predict accord, the thing that you're going to do is you're going to take the entire input sentence. That's going to be your X. The word that you just predicted, L, or you're predicting a couple of them, maybe 12 of them. That's going to be your beam search size. And then for each one of those, you're going to predict a corresponding second word. That's going to give you a lot of options, because for each one of them, you can pick 12 more, and it's going to give you 12 times 12. It's going to increase exponentially. But then to go to the next word, you're just going to select the top 12 outcomes out of these outcomes, out of all of those 12 to the power 2 possibilities. And then you keep repeating that pattern. And that is called beam search. So once you know your probabilities, you can do beam search to find the maximum. It's an approximate maximum. It's a greedy algorithm. So does this step make sense? The translation task, at least when it comes to inference. If I give you a model with some parameters, you're going to be able to use that to do your translation. Is this clear? Give me a couple of pieces. Okay, beautiful. Now the question is, what is this P? How do you model it? And how do you parameterize it? And this is where we are going to get creative. At that time, we were using RNNs and encoder-decoder type of architectures. You take your entire input sentence because you can take a look at your entire input sentence. You have that information in front of you, and then you can translate it. This is not an online translation. The sentence is already out there, and then you want to translate it. So we typed our sentence in Google Translate fully, and then we are going to press a button. Now translate that. You turn your entire input into a vector that's going to be summarized in C. The probability of your entire translation, you can use the chain rule for probabilities. You break it down into pieces, and then you are going to put another recurrent neural network to model this probability. There is also this idea of attention, which is rather than taking your input sentence and giving you a single vector to work with, take your entire sentence and give us as many C's as we have translation, as we have words in our translated sequence. So make this T dependent. And the way that you're going to do it is that you have a budget of 1 for your attention, which you can enforce that to add up to 1 using softmax. And then you're going to spread the amount of attention, which is 1 that you have, among your input sentence. How much attention should I pay to the first word or the representation out of a couple of BiLSTM layers? How much attention should I pay to that? The second word, the third word, the fourth word, while predicting the current word in the translation. The rest of it is just recurrent neural network. We covered it before. There is this max out nonlinearity in the end, which is a minor detail. Now you have modeled this probability of the target sentence given the input sentence. It means that now you have your probability, you have your likelihood, you can maximize your likelihood. The way that things work is that you first write a probability distribution. Out of the probability distribution, if you take that probability distribution, evaluate it at a single data point, that's going to tell you how likely that data should be. And then you are going to increase that data being more and more likely through the training process. Once the training is done, you have a model. Now it's time to measure its performance. You're going to use BLUE score. And BLUE score also takes care of the reference translation, the candidate translation having a shorter length compared to the reference translation. The problem is there is a bias towards your algorithm giving you shorter and shorter translations. And why is that? Because these probabilities are numbers that are bigger than 0, less than 1. And once you multiply them together, and remember, you're looking for higher probability sentences. If your sentence is shorter, you are multiplying less numbers that are less than 1 together. And therefore, you have a bias that's going to give you a larger probability value compared to multiplying a lot of numbers that are less than 1. So there is a bias in the algorithm towards shorter length sentences or shorter length translations. And then you can unbias that, at least when it comes to your scoring and BLUE score. There is more details in the YouTube video and this other YouTube video, which is really good on BLUE score. So watch that. And the problem is usually for a source sentence, there is multiple good translations. It's not like image classification that you have only one good class or one correct class. Here you can have multiple good translations and they're equally as good as each other. So was everything clear? I spent a little bit more time on this paper. The reason for it is because it is fundamental. It's going to give you all the pieces of the puzzle.
So how does the idea of align exactly work? Because I mean, especially the other language could have a different ordering of words and even more number of words than what was in the original sentence of English, let's say.
That's actually a very good question. So your question is, my input sentence could have a length of tx, my target sentence could have a length of ty, and they could be in different order. For instance, this French sentence, especially European economic area, is going to become zone economic open. So everything is reversed. How do you take care of those?
Yeah.
To take care of the first problem, you take your, at least in this model, we are going to see different solutions, but this is a fundamental problem. The question is fundamental. We can end up with different solutions. This is one solution. You take your entire sentence, you encode it in a single vector for as many vectors as you have in your output sentence.
Okay.
That's the way that you're going to handle that. And then that C is going to go inside your architecture. So you're always going to remember your entire sentence. To
I
answer
see.
your other question about the word order being messed up when it comes to translation, you have this attention mechanism. And as you can see, throughout the training, the attention mechanism is learning to attend in a reverse order to these three words. So what we are plotting here are actually these alpha values.
Okay.
And remember, for each output sentence, which is for each output word, you have as many alphas as you have input words. Basically, while predicting economic, what words are you paying attention to the most? And then these are the two highest values for your alphas. And that's why
Okay.
attention is beautiful. It's gonna take care of the words being in different order, and at the same time taking care of these input sentence having a different length. You just summarize it into multiple vectors.
So for the first problem, if we go with the approach of summarizing it into vectors, and the number of vectors would be, you were saying, would be as equal to in the what's there in the target sentence, right?
You have two options. One of them is one single sentence for the entire, one single vector for the entire
Yeah.
input sentence, like what you
Yeah.
were doing with classification.
Yeah.
Just summarize the entire sentence in a single vector.
Yeah.
Or if you go the attention route, summarize your entire vector, entire sentence in as many vectors as you have output.
But how will inference work there? Because for inferencing, we'll not know how many words are there in the output, right?
Oh, inference is dynamic. Inference, you are gonna predict one word at a time.
Okay. Okay. Oh, till the end of end tag. Okay. Makes
Then then
sense.
then you know
Yeah. Yeah. Yeah.
it's always gonna be one. Given the input sentence and
Yeah.
these three words, predict the next one.
Okay. Yeah.
And
Makes
then
sense.
given the outcome, predict the next one. And this is
Yeah.
where the beam search is gonna come in.
Okay. Yeah. Sounds good. Yeah.
So these are great questions. And these are fundamental questions. Later on, we are gonna come up with different solutions to the same problems. Any other questions? Okay, perfect. So make sure that you watch this video, both of them, this one and the one for this slide, because I'm gonna go into more details about the architecture. Now you're gonna understand attention a little bit more.